Good morning. Please let me know if my audio is clear. Good morning. Please let me know if the audio is clear. I'm using the maximum sound over here. Fine. Let us start today's class. Yesterday, if you remember, we were dealing with the concept of flow through pipes. We have discussed the concept of flow through pipes. Today, we are going to start the next topic, which is known as turbulent flow. The next chapter's name is turbulent flow. Let me write the date first. Today is 14th. The chapter's name is Elementary Turbulent Flow. Elementary Turbulent Flow. Elementary Turbulent Flow. Now, importance wise, this is the least important topic in entire internal flow. Okay, very less importance is there. Today we'll try to finish off this entire chapter. It is very small topic, very small topic. Now, regarding turbulent flow, let me tell you, as such, turbulent flow is a very lengthy topic. But from our examination point of view, we are having a very little amount of syllabus in turbulent flow chapter, right? Most of the chapter is supposed to be actually research-based chapter. It is supposed to be having more of experimental kind of study. But over here, we are not going for all those things. From examination point of view, what we are going to have are only few formulas you are supposed to remember and some basic fundamentals of turbulent flow. Let us first of all start with the definition of turbulent flow. Let us start with definition of turbulent flow. The definition of turbulent flow goes something like this. A highly unsteady flow in which inertia force dominates over the viscous forces. Okay, so you're going to have inertia forces dominating over the viscous forces. Let me do one thing. Instead, let me use the word over here, indisciplined flow. A highly indisciplined flow. Indisciplined flow in which inertia forces dominate over the viscous forces. Okay, such a flow is called as turbulent flow. Now, whenever inertia forces are going to dominate over the viscous forces, please understand what is the result going to be. Whenever these inertia forces dominate over the viscous forces, that time the fluid particles will move from one layer into other layers. Imagine there is a particular layer over here. Let us say this is some layer 1. This is some layer 2. Likewise, I'm having n number of layers. What was happening in laminar flow? In the case of laminar flow, any fluid particle from this particular layer was remaining in that particular layer only as you move forward. But now in the case of turbulent flow, this particle tries to leave its layer, go into some other layer. Let us say it is leaving the layer, going over here. So first thing that is going to happen in these cases is the viscous forces are going to be very weak. Therefore, the fluid particles will try to move from one layer to other layer. Intermixing of fluid particles will take place. Once this intermixing of fluid particles takes place, then what is going to happen? Random collision will take place and continuously the velocities keep on changing. For every fluid particle, the velocities keep on changing. This is one standard result of turbulent flow. So let us see all these things in characteristics. Characteristics of turbulent flow. Characteristics of turbulent flow. The first characteristic is high kinetic energy and high Reynolds number. High kinetic energy and high Reynolds number. This is the first characteristic you're going to have. Second characteristic, intermixing of fluid particles between the layers takes place. So intermixing of fluid particles between the layers. So this is the second characteristic you're having. What is the result of intermixing? Now, whenever intermixing takes place, eventually you're going to have random fluctuation in velocity for fluid particles. So third point over here is random fluctuation of velocities of fluid particles. Random fluctuation of velocities of fluid particles is going to take place. Take it. Apart from these things, one important characteristic. One important characteristic is friction factor is no more depending only on Reynolds number. Please remember, friction factor will depend also on surface roughness over here. So friction factor. Remember Darcy friction factor, right? That friction factor is going to depend on both. What are the both things? One is Reynolds number and surface roughness. Surface roughness. This surface roughness is represented by epsilon. We'll have a detailed discussion regarding that as we move forward. After this thing, next point you are supposed to remember is, in the case of turbulent flow, please remember that Newton's law of viscosity is not sufficient to identify the shear stress. So next point is Newton's law of viscosity. Newton's law of viscosity is not sufficient to identify the shear stress. So apart from Newton's law of viscosity, you'll have to deal with something else also. One more term is going to be developed apart from Newton's law of viscosity. So these are some characteristics of turbulent flow. Okay. After having seen all these things, now we are going into some more important concepts in turbulent flow. Okay, you can take a snapshot quickly of this particular slide. You can take a snapshot of this slide. This is the first slide for today's class. Now this slide, I'm going to discuss about velocity of a fluid particle in turbulent flow. This slide is going to be slightly mathematical in nature. Let me mention the side heading over here is velocity of a fluid particle. Velocity of a fluid particle in. Now when I write TF, please understand it is turbulent flow. Velocity of a fluid particle in turbulent flow. Now we have already mentioned that velocity of a fluid particle is supposed to randomly varying with respect to time. Okay. The reason for this random variation is because of random collisions taking place in turbulent flow. Whenever a particle is leaving its layer and moving to other layer, it will start colliding. Once collisions will take place, random collisions are taking place. So automatically you're going to have random fluctuation in velocity as well. This is understood. Now we want to analyze that velocity. To analyze that velocity, what I'm going to do is I'm going to start with a graph. Let us say over here, I'm drawing a graph of velocity with respect to time. Let us say I have chosen a component of velocity u over here, and this is over here time. Okay. I'm observing how the velocity u, that is the x component of velocity, is varying with respect to time. So this graph is regarding variation of u with respect to time. This is what we are discussing in this particular graph. Now what happens? Okay. Now whenever you're having a turbulent flow, that time the velocity is supposed to randomly vary with respect to time. There is going to be some random variation with respect to time. Let us say some random variation like this is taking place with respect to time. Now I'm observing, let us say till a particular time instant. The time, let us say, is equal to capital T time. I'm observing up till capital T time. From time t equal to 0 up till capital T, I'm observing over here. Chali. Now, since the velocity is randomly varying, it is for sure difficult to analyze this particular velocity. So I find that analyzing this particular velocity is very difficult. So now I have to think mathematically. What I'm going to do is I'm going to break down this velocity into two components. I will say velocity u at any random time is a combination of two velocities. One is u bar, the other is u prime. Is a combination of two velocities. One is u bar, the other is u prime. U over here is the velocity, local velocity, or a particular particle's velocity. U bar over here is known as U bar over here is known as, once again, U bar over here is known as time average velocity. Time average velocity. U bar is known as time average velocity. I'll help you understand all these things, don't worry. And U prime over here is known as random fluctuating velocity. Random fluctuating velocity. U bar is time average velocity and U prime is random fluctuating velocity. Now, what do we mean by these things? You see, from time t equal to 0 till t equal to capital T, my velocity is keeping on varying like this. So now let us say I take an average value of this velocity. I take an average value of this velocity. Suppose this over here is representing average velocity I'm having. Okay, the red line over here is representing average velocity. So let us say till here whatever I'm having, let us say till here whatever I'm having is known as average velocity. This is known as average velocity, u bar. And what is u prime over here? Now you see, there is going to be some fluctuating part also with respect to average velocity. That fluctuating part is known as u prime. For example, if you look over here, in this particular case, the fluctuating part is going to be equal to this much part. This part over here is equal to u prime part. This part over here is u prime. Now you have to understand this thing that u prime is going to be positive. U prime will also be negative. In some places you see u prime is going to be negative also. You are having a negative u prime also. Over here u prime is negative. And let us say at this particular time, the value of u prime is 0 also. So u prime will be positive, u prime will be negative, and u prime will be 0 also. All three things are going to be there. Okay? So these two velocities we are going to break down into. Now I have to develop the formula for u bar and I have to develop the formula for u prime. Both these formulas I have to develop. How to develop the formula of time average velocity? Very mathematical concept. You see, whatever is the area under this black randomly fluctuating line, same area should be under this red line. Then only I can say the red line is the average value of this black line. Please imagine that under this black line, you're going to have certain area. There is going to be certain area over here. Let us say I take a small thickness over here. I take a small thickness. Suppose this thickness is equal to some dt thickness. The thickness is equal to dt thickness. So now I can say area under velocity graph. Area under velocity graph has to be equal to how much? It has to be equal to integral of this small area. What is the small area over here? Let us say this velocity is equal to u and thickness is equal to dt. So I can say it is equal to u times dt. And it is ranging from where to where? It is time t is ranging from 0 till capital T. So I can say the range over here is from 0 to capital T. Let me save it as some equation number 1. Equation number 1. Now I can say area under this red line has to be equal to how much? The same thing has to be also equal to, it has to be also equal to, this velocity is u bar. So u bar multiplied to what time are we looking at? We are looking at a time of capital T. Capital T. Let me save it as some equation over here too. Now I know that equation 1 and equation 2 are supposed to be same. Both of them are same equations. So from here I can write, integral of u dt ranging from 0 to t is equal to u bar times capital T, which implies the value of u bar, has to be equal to 1 by t integral of u dt, where time is ranging from 0 till capital T. This is the formula for time average velocity. This is the formula for time average velocity. Let us take this formula as formula A, formula for time average velocity. Now, next thing, I want to look at the value of random fluctuating velocity. The problem with random fluctuating velocity is the name itself is suggesting it is fluctuating in nature. So now I try to think of time average of random fluctuating velocity. Let us say I'm imagining what will be the time average. What is going to be the time average of random fluctuating velocity? Time average of random fluctuating velocity. Random fluctuating velocity. What is going to be the time average of random fluctuating velocity? You see, the concept of time average, you please understand over here. Time average will be in the form of 1 by t integral 0 to t something times dt. What is that something? Whose ever time average you want to find out, you put that something over here. So going by that particular logic, I can say over here that u prime bar. You see, u prime bar means what over here? U prime is random fluctuating. Bar means time average of random fluctuating velocity. How much is it going to be equal to? This is going to be equal to same format, 1 by t integral 0 to t. Now, whose time average I want? I want u prime's time average. So u prime times dt. This is supposed to be the value I'm having. So u prime bar is equal to 1 by t integral 0 to t u prime times dt. Now, if you observe this particular value, okay, if you have some idea of mathematics, if you have some idea of averages, then you can straight away say this value actually has to be equal to 0. This value should be equal to 0. It will be equal to 0. The reason is u prime dt is basically the area of this u prime with respect to the red line. Now, if the red line is average, whatever is the area above will cancel off with the area below. So above area is positive, below area is negative. So both of them will cancel off. If both of them are canceling off, what will happen? Ultimately, this integral is going to become 0. As a matter of fact, please remember, time average of any random fluctuating velocity has to be equal to 0. That means u prime bar has to be equal to v prime bar has to be equal to w prime bar. All of them have to be identically equal to how much? 0. All of them have to be identically equal to 0. This is basic mathematics. Okay. There is no physics involved in this thing. The mathematics says that whenever you are having a mean value, the deviation from the right hand side and the deviation from the left hand side must be algebraically same. So therefore, the positive deviation will nullify with the negative deviation. Same concept over here. The upper part is behaving as positive deviation. The lower part is behaving as negative deviation. Both of them will get nullified over here. That is why integral u prime dt is supposed to be equal to 0. So from there, I can conclude this thing. Now you see, think from engineering point of view now. You see, for turbulent flow, it is very important for me to analyze the concept of fluctuating velocity, because turbulence is signified by its fluctuating velocity. But the problem I'm having over here is time average of random fluctuating velocity is coming out to be 0. The reason for it to come out to be 0 is because one part is positive, one part is negative. Now, if I ask you, can you still give me any idea of this fluctuating velocity? Then I can say that let us make the negative part also positive. If I make the negative part also positive, that can be done by squaring this thing. Imagine if I square u prime. If I square u prime, the positive part will be positive. Negative part also will become positive. So let us say, I'm going to next slide for a moment now. I can write, let us say u prime, one second, u prime square bar. Now, what is this? How do you read this thing? You see, look at the top. That is average of square of random fluctuating velocity. So this is average of square of random fluctuating velocity. Now, average of square of random fluctuating velocity. How do we write this thing? I'm not looking at the previous slide. I'm thinking mathematically now. Average is written like this. Please observe. How am I writing? 1 by t integral 0 to t dt. This is a format of writing average. Of whose average you want? U prime square's average you want. So let us write over here u prime square. That's it. U prime square. This is what is the meaning of average of square of random fluctuating velocity. Now this value will not be equal to 0. This value cannot be equal to 0. Why cannot be equal to 0? The reason is you have squared this random fluctuating velocity. That means the lower part, which was below, it also has become above now. it also has become above over here. So this is the value I'm having. Now, till here, everything is fine. This is helping me understand the concept of fluctuation. Let me mention over here, what is this representing? This over here is representing average of square of random fluctuating velocity. Random fluctuating velocity. Average of square of random fluctuating velocity. Now imagine, please imagine that this value, if you look at its units is going to be meter square per second square. Because you see, time and time cancel off, u square is remaining, that is meter square per second square. If I want to get the value in meter per second, then how do I do that? The only answer is you have to put a square root over here. So let us now put a square root to this thing. So you have a square root of u prime square bar. If I write the entire formula in sequence, first I'm going to write square root. First I'm having square root. Then average. Average means 1 by t integral 0 to t dt. This is average. Whose average I want over here? U prime square average. Now this value over here is a very, very important formula. This is a very, very important formula. Look at the sequence of events happening over here. That sequence is important. The first thing I have written is square root. Then I have written mean, that is average. Then I have written square. So this is root, then mean, then square. So this is RMS, RMS, root mean square. Whose root mean square? Root mean square of average, root mean square of random fluctuating velocity. Of random fluctuating velocity. Root mean square of random fluctuating velocity. This formula is again an important formula. Save it as some equation B. You are supposed to memorize this particular formula. So now we have seen two formulas over here. One formula was talking to me about whenever a particle is in a turbulent flow, whenever a particle is in a turbulent flow regime, that time that particle is supposed to have some time average velocity. How much is the time average velocity? This is time average velocity. Then that particle will have a fluctuating velocity whose mean value is given by RMS of random fluctuating velocity. Whose mean value is given by RMS of random fluctuating velocity. Please understand, whenever you go for RMS, the logic in going for RMS is very simple. You see over here, you will go for RMS when you are having positive deviation and negative deviation, both of them. But if you look at the average value of deviation, mathematically it comes out to be zero because positive is nullifying with negative. Now, so as to make negative deviation also positive, what you end up doing is you square everything. So negative value also is becoming positive. So let us say this value also is becoming some kind of peak. And then you put a square root so as to scale it back to the actual value. You first of all squared it up. You have to scale it back. Therefore, you're putting square root over here. So this is the logic for your RMS of random fluctuating velocity. Okay. Chali. Now, after having mentioned this point, there is one more thing I have to mention over here that is known as intensity of turbulence. This over here is intensity of turbulence. Next thing is intensity of turbulence. This intensity of turbulence I is equal to how much? What is the value of intensity of turbulence I? The value of intensity of turbulence I is 1 by V root over of 1 by 3 into u prime square bar plus v prime square bar plus w prime square bar. Okay, this is the value you are going to have for intensity of turbulence. 1 by V. Let me put a better V over here. This is capital V. 1 by V integral of, sorry, a root over of 1 by 3 U prime square bar, V prime square bar, W prime square bar. What is this V over here? This V over here is equal to root over of 1 by 3 U bar square plus V bar square plus W bar square. This is the value I'm going to have. Now please look at what is this signifying over here. Look at the numerator. Okay, forget about V. Look at the numerator over here. It is root mean square. Again, sequence dekhiye aap. Sequence is important. First you are putting square root, then you are putting average mean, then you are putting square. So this is root mean square. Root mean square of which velocity? All the three components, x, y, z, all three components combined. And what is this particular V over here? This V over here is in a way talking about average velocities of all three components combined. So this intensity of turbulence is talking to you about, effective ratio of fluctuating velocity to average velocity in all three directions combined. So this intensity of turbulence is the effective ratio of fluctuating velocity to average velocity. In which direction? In all three directions combined, we are looking at this thing. So this completes the first concept. It is regarding the analysis of a single fluid particle whenever it is under a turbulent flow regime. That fluid particle is going to have three significant values. One value is its time average velocity. That is in the previous slide. You have taken that down. The second value is going to be the fluctuating velocities average, RMS of fluctuating velocity, which you are seeing over here in the form of BWIT. And the third concept is how much is that intensity of turbulence it is experiencing. That is going to give you how much fluctuating velocity per unit mean velocity it is going to have in all three directions combined, given by intensity of turbulence I over here. It is given by intensity of turbulence I over here. Okay, try to memorize these formulas. Whatever formulas I have mentioned over here, try to memorize. I'm going to mark this particular formula as formula C. Please memorize A, B, and C formulas. Okay, if you are understanding the mathematics, then it won't take much effort for you to memorize these formulas. If you are not understanding the mathematics, then you will have to memorize it by writing also. Okay. Some people might have come late. This is the first slide for today's class. Please quickly take down a snapshot. This is the first slide for today's class. Second slide is this particular slide. Velocity of a fluid particle. This is basically the first concept we are going to study. We have studied. You can take a snapshot. Third slide is this particular slide, just now I mentioned. Let us now move further. After having discussed the concept of velocity of a fluid particle in turbulent flow, I'm moving further to the next concept. This is regarding shear stress in turbulent flow. This concept is regarding shear stress in turbulent flow. Second. Shear stress in turbulent flow. Shear stress in turbulent flow. Now, first thing you have to understand regarding shear stress in turbulent flow. already we have an established equation which we studied in the first chapter, first class itself. We have studied something called as Newton's law of viscosity, right? So viscosity is going to contribute towards shear stress. That is something which is fundamental, which is understood already. The second thing is, in the case of turbulent flow, apart from the shear stress due to viscosity, there is an additional shear stress developed. This additional shear stress developed is due to turbulence. Whenever turbulence takes place, an additional shear stress is observed by the fluid particles. So now I'm going to write down that in statement over here. Apart from viscous shear stresses, viscous shear stress, comma, an additional shear stress due to turbulence is observed. Now please understand, this additional shear stress is not going to be present in laminar flow. This additional shear stress is due to what? If you see over here, this additional shear stress is due to turbulence. So this additional shear stress is going to be present only in the case of turbulent flow. Okay. So now if I write down this in equation form, then I'm going to have tau is equal to tau due to viscosity plus tau due to turbulence. Tau is equal to tau due to viscosity plus tau due to turbulence. Now regarding this tau due to viscosity, this tau due to viscosity we know is equal to mu into du upon dy. It is also known as, this is also known as laminar shear stress. Laminar shear stress. So this is having one more name. It is known as laminar shear stress. I am going to represent it by tau with the laminar over here. Tau with the laminar over here. So this is going to imply now to me that the value of tau has to be equal to tau laminar plus tau turbulent. Tau laminar plus tau turbulent. So we actually mean by this thing that even though the flow must be turbulent, but it is going to have some portion which will have laminar characteristics. Even though the complete flow might be turbulent, please understand the basic meaning of this equation is, even though the complete flow might be turbulent, but some portion of the flow will have what characteristics? Viscous characteristics. In other words, laminar characteristics. In other words, laminar characteristics. Now, come to think of it, that this laminar shear stress is having a defined formula. That formula is mu into du by dy, where mu is viscosity, du by dy is known as your rate of shear strain. Till here, everything is fine. But the problem arrives in tau turbulent. Tau turbulent is not having a defined formula. This tau turbulent is not having a defined formula. So now we have to talk about a formula, or we have to define some formula for tau turbulent. Now, this headache of defining formula for tau turbulent was taken by some people. So, three people have given three different formulas, but with the same result. Formulas might look different, but they are going to yield same result for us. Now, these three people were Reynolds, Boussinesq, and Prandtl. So these three people have given some formulas for tau turbulent. We are going to call each formula after their particular name. So now I'm going to mention over here. Tau turbulent is represented by three models. They are called as three models. Now, what are those three models? Let us see over here. Let me, 1 second. The first model I'm going to have, the simplest of all models, is known as Reynolds model. Reynolds model. Now, what does Reynolds model say regarding tau turbulent? What is Reynolds model saying regarding tau turbulent? Let us see. According to Reynolds model, the value of tau turbulent about xy plane, is going to be equal to rho into u prime into v prime. Now you see over here, how simple is this particular formula? When I'm writing tau about xy, tau turbulent about xy, I'm going to have density multiplied to fluctuating velocity in x, fluctuating velocity in y. Just by looking at this particular formula, you can decide what are going to be, what are the other formulas going to be. For example, tau turbulent, in YZ plane will be equal to how much? Again, it has to start with density. Then since I'm having Y, I should write fluctuating velocity in Y, that is V prime. Since I'm having Z, fluctuating velocity in Z, W prime. Lastly, I'm going to have over here tau turbulent in ZX plane is going to be equal to how much? Use the same logic. Density multiplied to fluctuating velocity in Z is equal to W prime. Fluctuating velocity in X is equal to U prime. This is what I'm going to have. So this is the formula for tau turbulent. You see, every formula is not defined for tau. Tau is a complete shear stress. We are defining the formula only for what? Tau turbulent over here. Tau turbulent are these formulas. You can take a snapshot. We'll discuss about the rest two formulas in the next slide. Quickly take a snapshot. I did not say u prime is equal to v prime is equal to w prime. I said u prime bar equal to v prime bar equal to w prime bar. Please understand this thing. I said u prime bar is equal to v prime bar is equal to w prime bar. Lot of differences there between those two things. Okay. Which part of flow is laminar and turbulent flow? We'll discuss those things as we move forward. Chali. Now that you have taken the snapshot of that particular slide, let us move further to the next model. Apart from Reynolds model, we have a particular model known as Boussinesq model. The second model is known as Boussinesq model. Boussinesq model. Boussinesq model for tau turbulent. Remember, every model is defined only for tau turbulent. Nothing is defined for tau laminar. Tau laminar is well established. It is having a definite formula already. According to Boussinesq, first of all, Boussinesq was a French mathematician. Okay, he came to a conclusion that why don't we represent tau turbulent just the way we are having tau laminar? So he said, let us write tau turbulent is equal to. Now, how did we have tau laminar? We had something called as viscosity. He said, let us take something called as eta over here, which is similar to viscosity, multiplied to, then you are having du by dy. So du by dy. So eta multiplied to du by dy. This is what he said. Then what is this eta over here? This eta over here is known as eddy viscosity. This eta over here is known as eddy viscosity. Eta is known as eddy viscosity. Now regarding eddy viscosity, you are supposed to remember one thing. Eddy viscosity is not a property of fluid. It is going to depend on the flow. Please remember this. Eddy viscosity is not a property of fluid. It is going to depend on flow. Imagine if you are having laminar flow, eddy viscosity will be zero. If you are having turbulent flow, eddy viscosity will develop. If the intensity of turbulence is increasing, then eddy viscosity will increase also. So please remember this thing. Eta is not a property of fluid. Not a property of fluid. Eta is not a property of fluid. Now, you can question Boussinesq, but what is the purpose of representing tau turbulent in this manner? It's a reasonable question. Okay, why are you specifically representing tau turbulent in this manner? Then he would give an answer something like this. You see, tau, one second, this marker is getting stuck in between sometimes. One second. He would say tau, which is equal to tau laminar plus tau turbulent, can be now represented something like this, which implies from here onwards you can say tau has to be equal to mu plus eta whole multiplied to du upon dy. So you are having tau is equal to mu plus eta whole multiplied to du upon dy. This is what we are having over here. Okay. Now one more thing, please remember, in the major part of flow, eta is going to be much greater than mu. In majority part of the flow, you will be seeing that the value of eta will be much greater than mu. Okay, that you will understand as we go forward into a particular graph later on. Now come to the last model. The last model over here is a third one, which is known as mixing length model or Prandtl's mixing length model. Prandtl's mixing length model. Mixing length model. Prandtl's mixing length model. Now, according to Prandtl's mixing length model, he said that the value of tau turbulent is equal to rho into L square into du upon dy the whole square. This is what he said. Okay. Now I'll tell you what is L over here, but right now just understand there is something called as L. Now what I want you to do is, I want you to compare this equation and this equation. I told you, even though the formulas might differ, they are supposed to result in the same value, is it not? So if they are supposed to result in the same value, compare these two things and then deduce the value of eta. From here, you can say the value of eta is supposed to be equal to how much? Cancel of 1 du by dy. So you're left with rho into L square into du upon dy. This is the value we are having. Now the question is, what is this L over here? What is this L over here? L over here is known as mixing length. L over here is known as mixing length. L is known as mixing length. It is known as mixing length. Now the value of L is equal to how much? I'll tell you what is mixing length. Wait on. The value of L is equal to K times Y. K over here is known as Kármán's constant. Kármán's constant. And Y over here is distance from wall of pipe. From wall of pipe. And Y over here is distance from wall of pipe. Okay. Now let me define what is this mixing length. Please imagine that you are having a pipe. Let us take a diagram for imagining better. Let us say you are having some pipe. This, let us say, is a pipe. This is the pipe, let us say. You are having some center line. Let us say you have a certain center line. Suppose this is center line we are having. Now there is a fluid particle I'm considering. Suppose I'm considering a fluid particle. This is a fluid particle I'm considering over here. This fluid particle, let us say, is at a distance of y from the wall of pipe. This fluid particle is at a distance of y from the wall of pipe. Now this fluid particle, according to turbulent flow, this fluid particle is supposed to intermix with another layer. So let us say this fluid particle is going, traveling and intermixing with some other layer. It is traveling. The blue thing over here is it is traveling with some other layer. So it has traveled this much distance and it has intermixed with some other layer. The distance traveled by the fluid particle to intermix, that is known as your mixing length. It is known as your mixing length. This mixing length is proportional to y. You see over here, it is proportional to y. So L over here, which is mixing length is basically, it is basically distance traveled to intermix. It is the distance traveled in order to intermix. And please remember, the value of L is supposed to be proportional to phi. After concluding till here, now you please imagine the condition near the wall. Just imagine a fluid particle which is very, very close to the wall. At that particular point, the value of y is virtually equal to 0. Fine, accepted. The value of y over there is equal to 0. If the value of y over there is equal to 0, the value of L automatically has to be equal to 0. If the value of L is equal to 0, automatically the value of eta is equal to 0, the value of tau turbulent is equal to 0. So now I can make a note. This note over here says that near the wall, one second, let me use a different ink. Near the wall of pipe, we know that the value of y is equal to 0, which implies if y is equal to 0, automatically the value of L is equal to 0. If L is equal to 0, the value of eta is equal to 0. If eta is equal to 0, the value of tau turbulent is equal to 0. All of them are going to be equal to 0. If these things are equal to 0, this implies tau naught. Tau naught means which shear stress? Wall shear stress. The value of tau naught has to be equal to only one shear stress. Which shear stress is it? It is supposed to be equal to your laminar shear stress. Or you can say it is equal to mu into du upon dy at y equal to 0. This is what you're supposed to have. Now from here I can conclude that no matter how strong the turbulence is, no matter how much ever strong the turbulence is going to be, one thing you are one second, no matter how much ever strong the turbulence is going to be, please remember that you are going to have at the wall of the pipe laminar characteristics. The characteristics are purely laminar near the wall of pipe. At the wall of pipe or near the wall of the pipe, you are supposed to have purely laminar characteristics only dominant. Please remember this thing. So till here, what have we mentioned? Okay, what is the summary of this entire shear stress concept? Okay, I'm starting the slide of shear stress. We have defined over here that we are going to have an additional shear stress due to turbulence developed. Okay, therefore Newton's law of viscosity alone is not sufficient. Now for that per turbulent shear stress, we have mentioned three models. First model was Reynolds model. Second model was Boussinesq model, which was the simplest case, which said that the value of tau turbulent is equal to eta times du by dy. Eta is an imaginary property, which is not a property of fluid though. It depends on the flow. After that, we have mentioned something known as Prandtl's mixing length model. So Prandtl's mixing length model gave this idea. It is talking about some distance traveled by a fluid particle to intermix, known as mixing length. Okay. Now at the wall of the pipe, what is happening? Everything is coming down to 0 in turbulent shear stress. but laminar shear stress still exists. So therefore, no matter how strong the turbulence is, but near the wall, you're only going to have laminar characteristics valid. So this is regarding the concept of shear stress in the case of turbulent flow. I hope this is clear to all of you. Will the strain rate be same in turbulent flow as you are having in laminar flow? No, you won't have the same strain rate as you are having in laminar flow. Okay, it won't be same, don't worry. You'll be seeing that in the velocity profile. If you want, you can take snapshots. This is the first slide for shear stress. Quickly take snapshots. I'll discuss about the thickness of pipe as we go forward. This is second slide. And this over here is a third slide. This over here is not 1, it is L, mixing length. This is L over here. Now let us talk about, a particular concept which is known as velocity profile. Small concepts now. Okay. Some theoretical questions are possible. This concept is known as velocity profile in turbulent flow. Along with this, we are going to see some formulas also for velocity profile in turbulent flow. Now, first thing you have to remember over here, first thing, turbulent flow experiences logarithmic velocity profile. Logarithmic velocity profile. Turbulent flow experiences logarithmic velocity profile. So let me underline this thing. So velocity profile is logarithmic. Second point over here. Okay. Please understand this. Near the wall, the variation of velocity is very strong. And as you move towards the center, the velocity profile is going to become almost uniform. Almost uniform. Therefore, this kind of velocity profile is also called as almost rectangular velocity profile. So I can say variation of velocity, variation of velocity is strong near the wall of pipe. Near the wall of pipe. Near the center of pipe, velocity profile is almost uniform. Almost uniform. Okay. Therefore, the velocity profile is also referred to as almost rectangular velocity profile. Almost rectangular velocity profile. Therefore, the velocity profile is referred to as almost rectangular velocity profile. Okay? So these are some points you are supposed to remember regarding the velocity profile in turbulent flow, and that I am going to show in a particular diagram. Wait on. 1 second, please. Imagine that you are having some pipe like this. Imagine there is some pipe like this. I'm taking a particular axis, let us say, or a particular section I'm considering. Imagine this is a section I'm considering. The velocity profile is supposed to be varying very strongly and then almost uniform. So this is how the velocity profile is going to be in the case of turbulent flow. In the case of turbulent flow, the velocity profile would be something like this. This is the velocity profile. Now observe over here. Is it not looking like a rectangle? Almost rectangle, is it not? So near the wall, you're having a strong variation, and toward the center, it is remaining almost a constant. This kind of velocity profile you're having is logarithmic velocity profile. Logarithmic velocity profile. Now what we are going to do is, let me first of all mention, this distance is your small r distance, any random distance, and this distance is your capital R distance. There is total radius you're having. Now what I'm going to do is, I'm going to represent I'm going to mention some formulas of velocity profile. But before that, let me mention some nomenclature. You are having U, which is known as local velocity. U is local velocity. U maximum is your maximum local velocity, centerline velocity, maximum local velocity. Then you're having V, which is known as average velocity. Average velocity. And you're having V star, which is known as shear or friction velocity. Shear or friction velocity. We have talked about the concept of V star previously itself when we were discussing fundamentals of internal flow. That time itself we have discussed regarding the concept of V star. Now let us talk about the velocity. You can take a snapshot of this particular slide. I'm going to give you some 3 formulas for these velocities. Chale, quickly take a snapshot. Now, the formulas for velocity I'm going to have. First formula. I have given a formula already, but still I'm giving again. That is the formula for shear velocity. The formula for shear velocity V star. What is the formula for shear velocity V star? The formula for V star is equal to V root over of F by 8. F over here stands for Darcy friction factor, or this is also equal to root over of tau naught divided by rho. Root over of tau naught divided by rho. This is a formula for shear velocity. The second formula, it is a relationship between u max, not u, sorry, v. One second. It is a relationship between u maximum v and v star. Relationship between u maximum, v and v star. I have mentioned what is u maximum, what is v star already. Okay, the formula now is something like this: u maximum minus v upon v star is equal to 3.75. It is equal to 3.75. Okay, these are all empirical formulas. That means there is no derivation for this. You'll just have to remember them like as they are. The next formula you are having, these are not exactly empirical, semi-empirical. Okay, चलिए, the next formula you're having is a relationship between uh, U maximum V and friction factor F. These three things: relationship between U maximum V and friction factor F. Over here, the formula is going to be, excuse me, the formula over here is going to be U maximum upon V is equal to 1 plus 1.43 root over of F. This is a formula we are having. And finally, you're having a formula. This is a formula, relationship between U maximum, U and V star. U maximum, U and V star. Okay. The formula goes something like this: U maximum minus U upon V star is equal to 5.75 log to the base 10 capital R upon capital R minus small r. This is a formula you're going to have. So these are some formulas for turbulent flow. Apart from these, many other formulas are there. But if you remember these formulas, you can manage your questions easily. Okay? You can take a snapshot of these particular formulas. Try to memorize these formulas. I have discussed the concept of shear velocity previously. It is an imaginary velocity term which is representing the value of wall shear stress in the magnitudes of velocity. Chali. After having discussed the concept of velocity profile along with the formulas of velocity, we are now moving forward to discuss the concept of something known as shear stress profile. The next concept is shear stress profile. Shear stress profile in turbulent flow. Now, regarding shear stress profile, we already know that in the case of any internal flow, you are supposed to have shear stress profile linear. Okay, we discussed this thing already. Tau has to be equal to minus dp upon dx multiplied to r by 2, which implies tau is supposed to vary linearly with respect to r. Tau is supposed to vary linearly with respect to r. So you are going to have linear shear stress profile. Apart from this thing, we also know that tau is equal to how much? Tau is equal to, it is going to have a combination of two shear stress. One is mu into du by dy, that is laminar shear stress, plus tau turbulent. We know these two things. So one equation is in the first line, second equation is the second line. Now I'm going to draw the shear stress profile. Let us see how the shear stress profile is going to look like. Let us say, one moment. Suppose you are having a pipe. One moment, please. Suppose you are having some pipe like this. Let us say this is the pipe you are having. If I look at the profile of shear stress at any section, if I look at the profile of shear stress at any section, it is going to be linear like this. Let us say something. It is going to be linear like this. But inside this shear stress, I'm going to have a combination. There is going to be a combination. Okay, 1 second. There is going to be a combination of shear stress. So you're going to have combination of shear stress. 1 minute. This part over here is going to be representing laminar shear stress, whereas this part over here is representing turbulent shear stress. So you're having two shear stresses. Net shear stress is having linear profile, but some part is going to have laminar, some part is going to have turbulent shear stress. So I can say like this. This part over here is tau laminar. So tau laminar. And this part is going to have tau turbulent. This part will have tau turbulent. A combination is going to be there. At any position, a combination of tau laminar and tau turbulent will be present. But now what we will do is we will divide this entire pipe portion into two parts. Let us say this is the first portion I'm having. Then I have second portion over here. Second portion I'm having. Rest of it is third portion over here. First, second, and third portion. The first portion over here is known as laminar sublayer portion. It is known as laminar sublayer portion. In laminar sublayer portion, what is going to happen? In laminar sublayer portion, laminar shear stress is going to dominate over turbulent shear stresses. So I can say tau laminar dominates over tau turbulent. This is that laminar shear stress or laminar sublayer portion. Regarding this laminar sublayer portion, some points are important. This is the most important region, laminar sublayer region. Okay, regarding that, some points I have to mention over here. The first point I'm mentioning over here is the thickness of laminar sublayer, the thickness of laminar sublayer, which is represented by delta prime. So basically the distance over here, this distance over here is represented by delta prime. The thickness of laminar sublayer delta prime, which is given by the formula delta prime is equal to 11.6 nu upon V star. Nu is kinematic viscosity, V star is shear velocity. This thickness over here is important to identify the roughness characteristics of pipe. Roughness characteristics of pipe. So this thickness delta prime, which is 11.6 nu upon V star, is important to identify the roughness characteristics of pipe. One more point, very important point, and very few books have mentioned this particular point. Please mark this point as important. This point over here is saying that the velocity profile the velocity profile. If you remember, for entire turbulent flow, velocity profile is logarithmic, accepted. But the velocity profile inside delta prime, that is laminar sublayer region, inside delta prime. Now, in this particular region, velocity profile, please remember, is almost linear. Velocity profile inside delta prime is almost linear. You're going to have almost linear velocity profile in this particular region. Please remember this thing. Okay, so these 2 points you are supposed to remember regarding the concept of laminar sublayer region. The second portion over here, if you see the second portion, first portion I have mentioned. Second and third, we just have to take down the names. Second portion is where tau laminar and tau turbulent, both of them are significant. That region is known as your overlap region. So second region over here is known as overlap region. Overlap region. What is going to happen in overlap region? In overlap region, tau laminar and tau turbulent are both significant. Come to the third region now. The third region over here, which is where tau turbulent is dominating over tau laminar. It is known as outer turbulent region. Outer turbulent region. In this outer turbulent region, what is going to happen? In this region, tau turbulent is much greater than tau laminar. So this is regarding the concept of shear stress profile. In this shear stress profile, you first of all remember you are going to have a linear shear stress profile that is established from a very old concept we have discussed in the chapter of fundamentals of internal flow. Second thing, you are going to have inside that linear region a combination of two regions. The combination of those two regions is going to be in this particular fashion, such that laminar will be dominant near the wall, turbulent will be dominant in the entire rest region. Okay, this is regarding the concept of shear stress profile. With this, we have completed the major part of this chapter. Okay, before we go any further, I want you to take down some questions. Before we go any further, just by these particular formulas, if you want to take a snapshot of this particular slide, I want to take down some questions. From your literature only, I'm going to take down some questions. One second, please. Yeah, you can look at this particular. This is page 16. This is page 16 from your material, CRPQ questions. Okay. If you want, you can take a snapshot quickly of this question number 7 and question number 8. Both of them are worth 2 marks. Question number 7 and question number 8. Both of them are worth 2 marks. This is there in your book. Okay, question number 7 and question number 8. You can take a snapshot if you want. Now, question number 7. It says that the shear velocity for a flow through a pipe is 0.05 meters per second. The velocity at a distance of 0.5 mm away from the surface inside a laminar sublayer is 1.25 meters per second. Kinematic viscosity of the fluid is how much? Mark this as a very good question worth 2 marks in your examination. Worth 2 marks in your examination. Let us see. I'm starting the question now. This question is question number 7. Chapter in your book is going to be chapter number 9. This is worth 2 marks in GATE examination. 2 mark question in GATE examination. The question is saying, let me again look at the question. The shear velocity for a flow. So shear velocity for a flow means he has given you the value of V star is equal to 0.05 meters per second. Okay, don't worry if you're not able to get the answer because formulas you might not remember right now. Then he goes on to say the velocity at a distance of 0.5 mm away from the surface. Please underline that phrase inside a laminar sublayer. So he says the velocity, okay, is equal to 1.25 meters per second at he has given you some distance of y over here. The value of y is 0.5 mm inside laminar sublayer. 0.5 mm at y is equal to 0.5 mm inside laminar sublayer. So this inside laminar sublayer part is very important. Inside laminar sublayer part is very important. Okay, so this is the given. What is asked over here? Kinematic viscosity is equal to how much? This is being asked over here. This is the question we are having. Let us solve this question. Very simple question, but worth 2 marks in examination. Why I like this question that much is, it is testing multiple concepts. This question over here is testing the concept of what is happening inside laminar sublayer. You see, inside laminar sublayer, first of all, you have to understand that the value of tau laminar dominates over tau turbulent, and the velocity profile is almost linear. Two things you have to understand over here. So in solution, I am going to first of all extend this concept further and mention 2 points. First point is velocity profile is almost linear. And second point I have to mention over here is, now the shear stress over here, inside over here, let us say shear stress at the wall over here. Please remember, some time back I told you that shear stress at the wall is supposed to be purely tau laminar. Shear stress at the wall is supposed to be equal to how much? Purely tau laminar. That is equal to how much? Mu into du upon dy at y equal to 0. These 2 points, theoretical points, are being tested along with the numerical. Okay, chaliye, let us start now. He has given me V star. I know that the value of V star has to be equal to root over of tau naught by rho. And tau naught I know is equal to mu into du by dy at y equal to 0. So I can say it is equal to root over of mu into du upon dy at y equal to 0 whole divided by rho. So from here it implies that the value of V star has to be equal to, what is mu by rho? It is nu. So therefore I'm having root over of nu multiplied to du upon dy at y equal to 0. This is what I'm having. Now it implies square on both sides. V star square is equal to nu into du upon dy at y equal to 0, which implies nu has to be equal to V star square whole divided by du upon dy at y equal to 0. This is what I'm having. I already know the value of V star. V star is known to me. How do I get the value of du by dy at y equal to 0? From here. Now imagine that this over here is the wall, and this over here is a distance. This distance is equal to y equal to 0.5 mm. Over here the velocity is equal to how much? 1.25 meters. I'm having a linear velocity profile. If I have a linear velocity profile over here, then tell me what is du by dy? du upon dy at vol, that is y equal to 0, has to be equal to this velocity minus this velocity, that is 1.25 minus 0 divided by the gap in between, that is 5 into 10 power of minus 4. Now put in the values, put in the values in SI unit. You will get the value of nu also in SI unit. Please check what is the value in SI unit. SI unit is going to be meter square per second. Everything I have mentioned in SI units only. Okay, I have taken this value of dy also in SI unit. You are supposed to get the answer in SI unit. Please start. Regarding this topic's importance in GATE, not that much important. Not that much important, but sometimes questions can come, and when they come for 2 marks. See, there is nothing called as important or not important nowadays, because you're having multiple sets. If you don't get a question in a particular set, the topic's question can come in the other set. Eight F slide. Someone wanted 8F slide. You can take down 8F slide. Very good. 10 power minus 6 you are getting. Swarangi Marathi, correct answer. Very good. 10 power minus 6. So the value over here is 10 power minus 6. Since he wants the answer in centimeter square per second, I can say it is equal to 10 power minus 2 centimeter square per second. He wants the answer in centimeter square per second. I can see the answer is 10 power minus 2 centimeter square per second. Okay. Where have I used this particular concept? I have used this concept over here. Please check. Where have I used this particular concept? I have used this concept over here. See, theoretical concepts are being used in forming a numerical. Easily worth 2 marks in examination. Okay. Shall you quickly finish this off? Now I'm taking the next question. I hope you have finished off till here. The next question is from your literature, the same page, question number 8. A pipe of diameter 100 mm carries water. That question. Chaliye. This is question number 8. If you have the literature, please go through the question once. This is chapter 9, question number 8. Those who are not able to find out the question, you can take a snapshot quickly from the slide I'm showing right now. The question says a pipe of diameter 100 mm carries water, and the velocities at the pipe center and at 30 mm from the pipe center. The velocities are mentioned. 1 second, please. The velocities at the pipe center and 30 mm from the pipe center are 2 meters per second and 1.5 meters per second respectively. The flow in the pipe is given to be turbulent. The wall shearing stress is how much? This is a slightly direct question, but again, it is worth 2 marks in examination. Okay. Especially from this particular chapter, whenever questions come, they come for 2 marks. They come very rarely, but they generally come for 2 marks from here. Okay. He has said that you're having a pipe of diameter 100 mm. That means the radius of the pipe is equal to 50 mm. 50 mm. He says the value of U maximum is equal to 2 meters per second. And he says the value of U is equal to 1.5 meters per second at a distance small r is equal to 30 mm. At a distance small r is equal to 30 mm. He says the working fluid over here is water, so density has to be equal to 1000 kg per meter cube. All this is given to you. Now, with this much information, he's asking you the value of wall shear stress is equal to how much. Now, look at all this data over here. Quickly write down the data over here. Quickly write down the data from here. And look at the formulas. Purely formula-based question. Tell me which formula are we going to use over here? He has given you U max. He has given you U. He has given you the value of capital R and small r. He has given you density. He's asking you the value of tau naught. What formula? Very good. The formula D we are going to use over here. That formula over here is U maximum minus U upon V star is supposed to be equal to 5.75 log base 10 capital R upon capital R minus small r. This is the formula we are going to use. Now, U maximum over here is equal to 2 meters per second. U over here is equal to 1.5. V star, I'm going to write it as root over of tau naught by rho. Rho is equal to 1000. This is equal to 5.75 log base 10 capital R. Now you see, if I write these things in mm, then also there is no problem because this is actually dimensionless. You see, mm over here, they'll get cancelled off. It is dimensionless quantity. So if I write in over here, it is no problem. So therefore, this is equal to 50 divided by 50 minus 30. Come on, solve for the value of tau naught and get me the answer. Everything is in SI units, so you're going to have 46.74 Pascal. Sorry, 47.74 is it? 47.74 Pascal. The answer you're supposed to get is 47.74 Pascal. Question number 4 from the slide I'm showing right now. This is page number 15 in that particular PDF. The pages, I believe, are jumbled up. I want you to look at this question number 4, please. Question number 4. Look at the question number 4, please. You can take a snapshot of the question. A fluid flows in 30 centimeter diameter pipe at a Reynolds number of 10 power 6 10 power 6. If the friction factor is 0.025, the thickness of laminar sublayer in mm is equal to how much? Okay, look at this question. The reason for taking this question I'll tell you later on. I hope all of you are getting tau naught is equal to 47.74 from here. Okay. This is question number 4 I'm taking, chapter number 9. Question number 4, chapter number 9. The question says the diameter of a pipe is equal to 30 centimeter. Let us say 0.3 meters. 0.3 meters is the diameter of the pipe. Let me look at the question again. Reynolds number is 10 power 6, friction factor 0.025. Reynolds number is 10 power 6, friction factor 0.025. All these things are given. The question is asking you regarding the value of delta prime, that is laminar sublayer thickness is equal to how much? This value is asking. Now, how to find this value? Recall the formula for delta prime. The formula for delta prime is 11.6 nu upon V star. That is equal to 11.6 nu upon V star. I can write as V root over of F by 8. If you observe over here, I know 11.6, I know F, I know 8. What I don't know is nu upon V. I don't know this value. But you see, he has given me diameter in Reynolds number. Let us make a use of this thing. How do we do that? I can write Reynolds number is equal to V into D divided by nu, which implies nu by V, which I don't know, nu by V, which I don't know, also happens to be equal to diameter upon Reynolds number. Diameter upon Reynolds number. This implies delta prime is equal to 11.6 divided by root over of F upon 8. It is root over multiplied to. In place of nu by V, I'm going to write D upon Reynolds number. Now please observe over here. He is asking you the value of delta prime in mm. He wants this value in mm. Now you see 11.6 constant, 8 constant. F and RE are dimensionless. If you take this also in mm, your answer will be in mm. F and Reynolds number are dimensionless. So let us say this in mm now. So what am I going to have over here? Delta prime is equal to 11.6 upon root over of F over here is 0.025 divided by 8 multiplied to, this is 300 by 10 power 6. Get me the value of delta prime from here. Please start. Get me the value of delta prime from here. 0.0622 is the value. 0.0622 mm. So it's quite easy. Now I'll tell you what is the significance of this question. Why am I considering this question? I want you to observe something. What I want you to observe over here is every data given to you are practically very common data. Diameter of pipe 30 centimeter, very common. Or generally commercial pipes diameters range from 20 centimeters up till 1.8 meters. Commercial pipes are going to have 20 centimeters till 1.8 meters diameter. So 30 centimeters is quite common. Reynolds number is going to be 10 power 6. That is also very common. With water, getting Reynolds number 10 power 6 is very, very easy. Okay. Common Reynolds number. Friction factor 0.025. That is also quite common. All this data given to you is pretty common. Okay. This is fine. That means if this is practical data, the answer for delta prime also is a very practical value. This is the general range of delta prime. It won't be even 1 mm. It won't be even 0.1 mm sometimes. You see, this is less than 0.1 mm. What I want you to do is I want you to visualize something. Imagine that you are having this as a center line of the pipe and this as the wall of pipe. This is the wall of pipe, and the distance over here, which is the radius, it is equal to, let us say, 150 mm. This radius is equal to 150 mm. Now I'm taking a small thickness over here, which is known as delta prime, and its thickness is equal to 0.062 mm. Now just imagine, in front of radius, this is not even present actually. Such marginal distance, it is as good as negligible value, very, very small value. Are you following this thing? That is why in this particular region, if it is a negligible value, if I have some velocity profile, in such a small distance, the velocity profile will look linear. That is the reason why sometime back, if you remember, we have mentioned that in the case of delta prime, in that region of delta prime, the velocity profile inside is going to be almost linear velocity profile. It is going to be almost linear velocity profile. I hope you are following this question over here and you're following the meaning of this linear velocity profile also. Let us now move further. Let us now move further. Now I'm starting the concept of something known as roughness in pipes. Let us now talk about the concept of roughness in pipes. Roughness in pipes. Now, let me define this thing. The average height of surface irregularities at the inner wall of a pipe is known as surface roughness. It is known as surface roughness, represented by epsilon. What do we mean by this thing? Let us draw a diagram to understand this. Imagine you're having a pipe's wall. This I'm looking at right now, the wall of a pipe. Let us say this is the outer wall, and the inner wall is going to be something. Let's say some irregularities you're having. You're having some irregularities over here. Okay. So let us say you're having some irregularities over here. This is the inner wall you're having. Okay. Of the pipe. Now this is going to have some average height. It is going to have certain average height, is it not? For example, if you see, it is going to have certain average height. Let us say, one second. It is going to have some average height. This average height of irregularities, is known as surface roughness, epsilon. Now the question is, what is the significance of this surface roughness? The significance of surface roughness is when turbulent flow comes in contact with surface roughness. When turbulent flow comes in contact with surface roughness, when turbulent flow comes in contact with surface roughness, then what happens? Then formation of eddies takes place. Formation of eddies takes place. Whenever turbulent flow comes in contact with surface roughness, that time you're going to have eddies taking place. Formation of eddies is going to take place. Okay. So you're going to have eddy formations taking place whenever turbulent flow comes in contact. Okay. With this much information, we are going into details now. Let us take a particular case. I'm taking. In this case, imagine that you are having the wall of the pipe something like this. This is the wall of the pipe, and let us say you are having surface roughnesses. You are having surface roughnesses something like this. This is the surface roughness, let us say. Furthermore, imagine that this distance over here is laminar sublayer thickness. This distance is laminar sublayer thickness. Epsilon value will be this much. This much value is epsilon. You see, epsilon is much lesser than delta prime. Okay, epsilon is much lesser than delta prime I'm having. Now what will happen? Over here, you are going to have turbulent flow taking place. You are going to have turbulent flow taking place. And since this is laminar sublayer region, you are going to have over here laminar flow taking place. You will have laminar flow taking place over here. This is a particular case we are having. This particular case, we are going to call it as hydrodynamically smooth surface. Hydrodynamically smooth surface. Hydrodynamically smooth surface. Now, hydrodynamically smooth surface means even though you are having surface roughness, but turbulent flow is not able to come in contact with this surface roughness. Even though surface roughness is there, but it is behaving as a smooth surface because turbulent flow is not coming in contact. Remember, turbulent flow should come in contact for formation of eddies to take place. Now, when do we say a surface is hydrodynamically smooth? We are going to say a surface is hydrodynamically smooth provided epsilon upon delta prime, epsilon upon delta prime is less than or equal to 0.25. That is when you are going to say the surface is hydrodynamically smooth. In this case, what is going to happen? In this case, straight away, your friction factor should become a function only of Reynolds number. Recall, friction factor was supposed to be a function of Reynolds number and epsilon in the case of turbulent flow. But epsilon is not creating any effect over here. Therefore, friction factor has become a function purely of Reynolds number. Over here, you are supposed to memorize two formulas. The first formula you're supposed to memorize, you have actually used this formula yesterday, I believe. That form, day before yesterday, the formula is F is equal to 0.316 divided by RE power 0.25. This formula over here is known as Blasius equation. Blasius equation. You have used this formula 2 days back, day before yesterday probably. Okay, Blasius equation. But this formula is valid only if Reynolds number is less than or equal to 10 power 5. Till then only you can use this formula. If the Reynolds number is exceeding 10 power 5, then what? Then you have a different formula. That formula for friction factor is given by 1 by root over of F is equal to 2 log to the base 10, 2 log to the base 10, RE into root F minus 0.74. Minus 0.74. This formula over here is known as Nicoratz's equation. Nicoratz's equation. Okay, it is known as Nicoratz's equation. Nicoratz's equation is valid for any Reynolds number. So these two formulas you are supposed to remember in the case of hydrodynamically smooth surfaces. Again, what is hydrodynamically smooth surface? A surface which is having roughness, but turbulent flow is not able to come in contact with that surface roughness. Such a surface is known as hydrodynamically smooth surface. Moving further, the next surface you are having, you can take a snapshot quickly of this particular slide. The second type of surface you are going to have is known as hydrodynamically rough surface. Hydrodynamically rough surface. Hydrodynamically rough surface. Now, what do we mean by hydrodynamically rough surface? In this particular case, surface roughness is going to contribute. In this particular case, epsilon upon delta prime is going to be greater than or equal to 6. Greater than or equal to 6. So imagine you are having a wall. Let us say surface roughness or something like this. Okay, I'm drawing a very magnified view. Surface roughness something like this, and delta prime is something like this. Delta prime is something like this. This over here is delta prime. Now you see surface roughness is easily coming in contact with turbulent flow. You see above delta prime, the complete flow is turbulent flow only. So turbulent flow is coming in contact with surface roughness over here. If it is happening, automatically the formation of eddies will take place. Eddy formations will take place over here. Now this particular case is known as hydrodynamically rough surface. Over here, the friction factor has to be a function purely of epsilon. It will be a function purely of epsilon. Okay, what is the formula given by over here? The formula is 1 by root f is equal to 2 log base 10 capital R upon epsilon plus 1.8. Capital R over here is known as radius of pipe. Radius of pipe. And epsilon over here is your surface roughness. Surface roughness. Epsilon over here is surface roughness. Okay, fine. Now, after having discussed this thing, there is one more possibility. One more possibility. You see, I have mentioned epsilon upon delta prime less than or equal to 0.25. I have mentioned greater than or equal to 6. There is one more possibility, and that possibility is when epsilon upon delta prime is greater than 0.25 but less than 6. This is known as pipe in transition. Pipe in transition. You cannot exactly call it as perfectly smooth, or you cannot exactly call it as perfectly rough. It is somewhere in between, transitional state. Okay, pipe in transition. In this particular case, what should happen? The friction factor over here should be a function of both Reynolds number as well as epsilon. Both Reynolds number and surface roughness are going to affect your friction factor in this particular case. So this is known as the concept of pipe in transition. Pipe in transition. So this, you can take a snapshot of this particular slide. This is regarding surface roughness concept. Surface roughness concept. Now, the last topic of this particular chapter. Okay, this chapter is going to close with this particular topic. This topic is known as commercial pipes. Commercial, TIAL, sorry. Commercial pipes. I don't know the spelling. Okay, you can adjust the spelling. Commercial pipe. Both the spellings are looking wrong for me. Okay, commercial pipes, what is going to happen in this particular case? C only is correct, probably. In the case of commercial pipes, someone is asking me regarding what are the formulas in transition. There are many formulas in transition. You don't have to memorize. As a matter of fact, see, you don't have to memorize Nikodym's equation over here and here also. One second, I did not give you, yeah, I gave you a formula over here, right? This is again Nikodym's equation. In examination, you don't even have to memorize Nikodym's equation. The reason is, in examination, they will give you the formula to use. Okay, I'll show you one question sometime later on. They will themselves give you the formula, what formula you're supposed to use in order to solve the question. Okay, someone is asking me regarding what is the word hydrodynamical over here. What is the meaning of hydrodynamic over here? That is a very good question actually. Okay, before going to commercial pipe, let me discuss the word hydrodynamic. Hydrodynamic. Why are we not just saying smooth? Why are we not just saying rough? Why are we saying hydrodynamically smooth, hydrodynamically rough? I'll give you the reason why. Look over here. Imagine you're having a particular pipe with some roughness. Okay, I bring you this particular pipe. Okay, some big pipe is there at the wall. I'm having this cross-sectional view. I bring you the pipe and I ask you, tell me whether it is a smooth surface or a rough surface. What should you answer? Your answer should be data is insufficient or I don't know right now. That should be your answer. Why? The reason is roughness or smoothness of a pipe is not just based on epsilon. When I give you a pipe, only thing you know right now is the value of epsilon. Only thing you know right now is epsilon, nothing else. You don't know anything else. Whereas roughness or smoothness is based on epsilon upon delta prime. Delta prime also is important. Recall the formula for delta prime. Epsilon upon delta prime means 11.6 nu upon V star. That means you can decide roughness or smoothness based on what? You can decide based on epsilon, nu, and velocity. These three things are required to decide whether the pipe surface is smooth or rough. It is smooth or rough. Now tell me, this is a property of what? Fluid. Hydro. This over here is dynamic. So fluid property and motion property both are required over here. Both are required over here. Then if this along with pipe property, all three things are required to decide whether it is a smooth surface or rough surface. Otherwise you cannot decide. Otherwise you cannot decide this thing at all. Okay. Moving further, one more thing you imagine. I bring a pipe to you which is having some roughness. I am bringing a particular pipe. Okay. I am going to make water flow from here. Let us say water is flowing mu1 at a velocity v1. Epsilon is constant. I say for my case, the pipe is behaving as a smooth pipe. Now you use the same pipe. You are using the same pipe with a different fluid nu2 at a different velocity v2. Who knows, for this particular case, it might behave as what pipe? It might behave as a rough pipe. That means a particular pipe is not decided as a rough or smooth pipe. A particular pipe in that particular flow conditions can be decided as a smooth or rough pipe. I hope you are following what I'm saying. You see, a pipe only has a property epsilon, but smoothness or roughness does not depend only on pipe. They depend on the fluid characteristics and the flow characteristics also. All these things combine and then decide whether it is a smooth or a rough pipe. I hope you're following. That means a single pipe can be a smooth surface in a particular flow. Same pipe can be a rough surface in a different flow. Same pipe can be a transition pipe in a different flow. I hope you're following this. I hope you're following this thing. And with this, I'm going to introduce the concept of what is known as a commercial pipe. Now imagine this is a commercial pipe itself. Let us now merge this concept with commercial pipe. This is a commercial pipe. Okay. Sometimes in commercial pipes, we have a different velocity condition. Sometimes we have a different velocity condition. It is not necessary that every time the velocity condition should remain same. So that means in a commercial pipe, it is difficult to identify whether the pipe is behaving as a smooth or rough pipe. It is difficult to identify. We can't always say that thing. Okay, sometimes it can be rough. Same thing can be behaving as smooth also. Therefore, for commercial pipe, we need a different formula. The formula should be slightly more complex. It should consider everything into picture and then get the value of friction factor in commercial pipes. Fine. So those formulas are present. They are highly complex formulas. You don't have to memorize those formulas. I will mention those formulas. Apart from this, in commercial pipe, finding the value of epsilon is very difficult. So therefore, what they do is they manufacture one more pipe. Okay, imagine, listen to this carefully. Imagine you are having a factory. In this factory, you're manufacturing pipes made out of steel. Your factory, you're manufacturing pipes made out of steel. Now you see, surface roughness is going to be the property of that particular material you're using and the manufacturing process you're using. Two things are going to determine surface roughness. Okay, one thing is what material you're using. One more thing is what is the manufacturing process you're using. If you have studied the concept of material science, you might be knowing that materials properties change with respect to the manufacturing process. So your surface roughness depends on these two things. But the problem is finding out this surface roughness is a very difficult task. Okay, it is as good as impossible task. Why? Dekhiye, you are measuring the average height inside the pipe. And these average heights are in microns. And they are not varying only with respect to the length of pipe, they are also varying with respect to the circumference of pipe. अब देखिए कितने variables आ गए यहाँ पे. So many variables. Finding this average height is not an easy task. एक तो you are going inside the pipe, difficult concept. Next thing, you are measuring something which is in microns. Next thing, that variation is taking place along length. It is also taking place along circumference. All these things make it so much difficult. That is why what we do, whenever you are having a particular plant which is manufacturing pipes, you manufacture one more pipe in your laboratory, which is known as your equivalent pipe. It is known as equivalent pipe. Now, this equivalent pipe manufacturing is very, very costly. Only one pipe you'll manufacture, equivalent pipe. This equivalent pipe is manufactured such that using uniform sand grain roughness. If you have seen a sandpaper or etching paper, we say, using that uniform sand grain roughness, you're going to manufacture the inner wall of the pipe. Uniform sand grain roughness will be there. You might have seen those sandpapers and all now. Okay? So using that sand grain roughness, you are going to manufacture. You will manufacture in such a way that your commercial pipe and equivalent pipe both have same diameters, both have same lengths, both are experiencing same discharge, and both are going to have same head loss. If everything for both of them is same, then the surface roughness also should be same. So whatever is the surface roughness of equivalent pipe, same surface roughness you are going to use for this particular steel pipe or commercial pipe. That surface roughness is known as uniform sand grain roughness or equivalent roughness. Yes, are you following all these things? Today's class was very boring for you, I understand. Topic of turbulent flow is like that. Yes, are you following all these things? The meaning of equivalent pipe over here. No response. Very good. No, very good. ठीक. 50%. I'll do one thing. Little bit bouncer. In 2 minutes, I'll again summarize this thing. Please try to understand. 1 second. First of all, I am by default assuming you have understood the meaning of hydrodynamically rough and smooth. I am also assuming that you have understood that a pipe can behave as a smooth pipe, same pipe can behave as a rough pipe. Because roughness and smoothness are not just dependent on epsilon, they also depend on nu, they also depend on velocity. Next thing, imagine you are having a pipe. This is a pipe which is a commercial pipe. Okay, commercial pipe. Finding epsilon difficult. तो क्या करेंगे आप? You will go into lab. You manufacture one more pipe. How do you manufacture? Diameter, same. Length and length, same. Discharge and discharge, same. Everything same. You make some flow pass through this thing, whose epsilon finding is difficult. But while manufacturing this particular pipe, you are going to manufacture with uniform sand grain roughness. Uniform sand grain roughness. You are letting some flow take place over here. You will keep manufacturing with uniform sand grain roughness, and you will see when will the head loss become equal. Let us say head loss did not become equal. Over here, head loss is coming out to be lesser, so you'll increase the roughness. Again lesser, you'll increase the roughness. Let us say at some particular point, head loss is becoming equal. The moment head loss becomes equal, you say that for same diameter, same length, same discharge, head losses are equal. That means their surface roughnesses are also equal. Epsilons are also having become equal. That means what? I did not put any effort to identify the surface roughness inside over here. Because putting effort over there is waste. You can't do that thing. What did I put effort in? I put effort in manufacturing different equivalent pipes. Initially, I put 11 micron. I did not get same head loss. Then I put 15 micron. I did not get same head loss. 20 micron. I got same head loss. Now I know that this 20 micron and over here also epsilon should have 20 micron only. This 20 micron now is known as equivalent sand grain toughness. Okay. Now, if you don't understand all these things, you will have difficulty not in examination, probably in interviews you'll have difficulty. If you're understanding, very good. If you're not understanding, don't worry that much. You struggle after examination. Okay. Right now, I can't go into same thing. I have to repeat if you want again. That is not possible. You look at the recorded videos if you want. I hope this is clear now. If it is still difficult, you look at the recorded videos. Commercial pipe. I'm coming back to commercial pipe. First point, finding surface roughness. My handwriting will not be neat now. Please adjust. Finding surface roughness is difficult. Therefore, an equivalent pipe of uniform sand grain roughness which is represented by epsilon s of uniform sand grain roughness is manufactured. See, one pipe you manufactured, that is sufficient. Then from your particular plant, from your particular factory, whatever pipes are going to come out, they'll have same roughness as long as material and manufacturing process are same. Okay, uniform sand grain roughness is manufactured. Okay, so it is going to be same for the commercial pipe as well as for equivalent pipe. Second point over here, the friction factor in commercial pipe. This is very important point. This point I'm going to stress on. I told you in commercial pipes, flow rates can keep on changing. अभी requirement आपका 100 liters per second है. Velocity will be different. Later on requirement, let us say, is 500 liters per second. Velocity might be different. You can use a pump, increase the discharge. Velocity will become different. That means that a flow can be sometimes rough. It can be sometimes smooth also. It can be sometimes transition also. So since it can change, now I have to find out a particular formula which is going to be valid in the case of rough, smooth, transition. Every pipe, single formula should be there. That formula of friction factor is given as a function of Reynolds number and epsilon s upon d. There are many formulas of this particular sort. Some formulas over here, one formula over here is known as, in this particular format, there are many formulas. One formula is known as Colebrook equation. He was the first person to have given such a formula. Then one formula was known as Halland's equation. As a matter of fact, Indians have also given a formula. Okay, there was a Swami and Jain equation. A particular formula is known as Swami. Okay, Swami. I'll write MI better. Swami and Jain equation. Many formulas. There are more than 5-6 formulas over here in this particular format, which are representing friction factor as a function of Reynolds number and epsilon s upon d. These kind of formulas are there. Memorizing these formulas, very difficult. No need to memorize, not required also. I'll show you one problem where such a formula is there. Okay, look at this particular problem. This problem we are going to solve now. This problem says air at 10 meters per second. Sorry, air enters a 10-meter long section of a rectangular duct, cross section 15 centimeter by 20 centimeter, made of a material. Now you see, he's saying that material is having a property. Surface roughness is equal to 0.45 mm. At 1 atmosphere and 35 degrees centigrade रहना है यहाँ पे. Density, kinematic viscosity, average velocity given. Disregarding entrance effect. इसका मतलब I'll tell you later on. Disregarding entrance effect. I'll tell you the meaning later on. Determine the fan power needed to overcome the pressure losses in this section of the duct. The following correlation might be used. This equation over here is Halland's equation. Now you see over here, friction factor is a function of Reynolds number. It is also a function of epsilon upon d. It's a function of epsilon upon d. This is a question from your chapter 8, question number 9. It is easily worth 2 marks. A slightly difficult question for 2 marks. Okay. Take down the data quickly. The given data over here. Is cross-section area, the cross section area over here is equal to how much? It is equal to 15 centimeter by 20 centimeter. It is 0.15 into 0.2 meter square. Epsilon value is equal to 0.45 mm, that is 4.5 into 10 power of minus 4 meter. Density is equal to 1.145 kg per meter cube. Kinematic viscosity is equal to 1.655 into 10 power क्या है वो -5 meter square per second. Average velocity of flow is 7 meters per second, and this is the formula you are supposed to use to solve to get the value of F. And you have to find out power fan required is equal to how much? Fan power required is equal to how much? This is the question asked over here. Very lengthy question for a 2-mark question. So we are going to make a sequence first of all. Okay, yesterday remember we have done some kind of sequencing. That sequence you are going to create over here. First of all, why is fan used over here? देखिए, fan or pump are used for overcoming losses. Whenever losses are going to be there, if you want to overcome losses, you are supposed to use a fan or a pump. Pump is used whenever you are having liquids. Fan or a blower is used whenever you are having gases. For gases, you don't require pumps. Fans are sometimes sufficient. So this fan power is basically whatever is the power loss. So let us say we want fan power. Power fan is basically equal to whatever is the power loss. Whatever the power loss, that is compensated by fan power. Now the question is, what is power loss? The formula for power loss has to be equal to rho into G into Q into head loss, gamma into Q into H. So rho G Q H. Now see what all we know. Rho we know, G we know, Q also in a way we know. कैसे पता है Q? देखिए क्रॉस सेक्शन है और वेलोसिटी है. You know the value of Q. What we don't know over here, head loss we don't know. We don't know the value of head loss. Okay, head loss is not known. चलिए एक स्टेप ऊपर जाइए अब. Head loss कैसे पता करेंगे? How will you find out head loss? For head loss, you need to know the value of FLV square by 2GD. FLV square by 2GD. L is given actually. L is equal to 10 meters. Given. L is equal to 10 meters. Now see in head loss formula, what all do we know? We know the value of L, we know the value of V, we know the value of 2G. We don't know D. Actually, D over here is D hydraulic. आपको सोचना चाहिए D over here is D hydraulic. Why is it D hydraulic? Why is it D hydraulic over here? The reason is you are not having a pipe, you are having a duct. SMA D hydraulic. So I have to find out even this value and this value. Now how do we find the value of F? Formula है यहाँ पे. But उसके लिए क्या चाहिए? To use that particular formula, what is required? Reynolds number is required. You have to find out Reynolds number. And then after finding Reynolds number, you have to find out F. And for finding Reynolds number, you require the value of D hydraulic. So first the sequence has been established now. First D hydraulic, then Reynolds number, then friction factor, then head loss, then power loss, that is equal to fan power. Very lengthy question. But still we'll finish this question now quickly. I hope this is clear to you. How to create a sequence. I hope it is clear. This is very important tool in examination. If you are not creating sequence in problems like these, then you will end up wasting a lot of time. To create sequence, half a minute is required. If you are smart enough, less than half a minute is required to create a sequence. Okay, now let us follow. Start with D hydraulic. I hope all of you have taken down the given data. I'm going to the next slide to solve the question. Let us start with D hydraulic first of all. D hydraulic is equal to how much? 4 times area upon perimeter. That is equal to 4 into 0.15 into 0.2. I'm waiting for your values, please. 0.15 plus 0.2. I do not have a calculator. I'm relying completely on you for answers. D hydraulic कितना है लिखिए? Point 171 meters. See, everything I try to take in SI units, ताकि ending में you don't have to worry about the units. Okay. Thank you, Chakrapani. Yes. After D hydraulic क्या है next task क्या है अपना? After D hydraulic our next task is to identify the value of Reynolds number. Reynolds number I can write is equal to V into D hydraulic divided by nu. V is equal to how much? 7. D hydraulic is equal to 0.171. Nu over here is equal to something value here na, whatever value 1.655 into 10 power of minus 5. You check this, get me the value of Reynolds number quickly. Reynolds number please. I'm looking for Reynolds number now. Reynolds number क्या बात कर रहे? 725 बहुत कम है, नहीं होता. 72326. I'll take this value. अच्छा दिख रहा नंबर 72326. 72326 is a Reynolds number value. Reynolds number value. Okay, 72507. Okay. Row is not missing. Don't worry, sir. I wrote mu over here. I did not write mu over here. Okay. Jerry is giving 725. Okay, somewhere over there. Now I want you to use this to get the value of f. 1 by root f formula you use from here. Whatever formula you're having, use from this particular slide. Get me the value of f. Now this will take some time for you probably. Get me the value of f up till 4 decimal places. Again, I'm emphasizing 4 decimal places chahiye mere ko. 4 decimal places. The value of f 4 decimal places, please. Please start. Up till 4 decimal places, get me the value of f. Please start. Question slide. This is this slide. Up till 4 decimal places, get me the value of f. Akash has given me 0.01926. Okay, I'll take that as answer if anyone else is also getting the same thing. Someone please confirm. D over here is D hydraulic. देखिए आप डक्ट में काम कर रहे, ऑटोमेटिकली यू शुड नो D is D hydraulic. जहां भी D देखते हैं आप D hydraulic लिख देंगे. D hydraulic, just now we have found out na sir, D hydraulic 0.171 meters. Come on, कैलकुलेटर से काम करना है यार. This is not, D does not mean hydraulic mean depth. It means hydraulic diameter. Hydraulic depth is different, hydraulic diameter is different. Okay. Arey yaar, I'm getting very different answers. Everyone is giving different answers. The most common answer I'm getting over here is 0.02699. I'm taking that answer. 0.02699. I'm taking that as answer over here. Right. I've got many of you giving me the same answer. 0.02699. Okay, friction factor is known to me. What next? Sequence देखिए अब. What next after friction factor? Head loss. Head loss is equal to how much? Head loss over here is equal to FLV square by 2GD hydraulic. F is there, L is 10. So let me write the numbers over here. 0.02699. Length is equal to 10. Velocity is equal to 7. 2 into 9.81. D hydraulic is equal to 0.171. Come on. Use this value of F and get me the answer for head loss. Please be quick. This value of F. I hope you are taking this value of F. 3.94 meters, you see.
3.94 meters of air. Now that means the value of power loss is equal to how much? Whatever is the power loss, fan has to apply the same power. So it is equal to density into Q into G times head. So density over here is equal to how much? He gave some density value. Previous slide you see density value he gave 1.145 है ना. So 1.145 लिख लेते हैं. 1.145. Discharge is equal to cross section area into velocity. Cross section is 0.15. Velocity is 0.2. Sorry, into velocity is 7. G is 9.81. Head loss is equal to 3.94 meters. 3.94 meters. Get me the value of power loss. 4.73 watt, is it? Okay, no, 9.29 watts. Okay, I'll take answer as 9.29 watts as answer. Answer I'm taking as 9.29 watts. You see, this much of power is lost by the fluid. Now, if it is lost by the fluid, you should supply this much of power from your external source so that the fluid can steadily move. That external source over here is fan. That external source over here is fan. In the case of liquid generator, it is pump. Why don't we use pumps over here? You see, for 9 watts, you don't require a pump. Your exhaust fan is going to produce this much of power very easily. Okay? That is why pump is fan is sufficient over here. So this is, you see, we were mentioning, one second, let me come back over here. I told you in the case of commercial pipe, friction factor is represented like this. So you have multiple equations. The most primary equation is Colebrook equation. Colebrook equation is the first equation and most complex equation of this particular sort, which has been, later on it has been simplified in the form of Halland's equation, Swami-Jain equation, many more equations are there. All those things are there. Next thing, last point over here is Colebrook equation has been converted into a graphical form. That graph is known as your Moody's chart. The graphical representation of Colebrook equation is known as Moody's chart. It is known as Moody's chart. Now, what is this Moody's chart? I have saved one slide which is showing Moody's. One second, sorry. This is Moody's diagram or Moody's chart. Look over here at this diagram. Very interesting chart. Okay, and you see, whenever you're having functions of two variables, that time you're supposed to have charts like this. Okay, you see, the problem we are having is f is equal to a function of Reynolds number and epsilon s upon d. It's a function of two things, Reynolds number and epsilon s upon d. If it is a function only of Reynolds number, drawing a graph is very easy. But since it is a function of two things, one is Reynolds number, the other is epsilon s upon d, now the problem becomes slightly complicated. What do we do? How did the first person to have constructed this chart, what did he think? Okay, think like him now. He thought function of two variables. Function of two variables complex than function of a single variable. So his logic was, let us do one thing. Let us fix the value. Let us make this value constant. If we make the value constant, what does this imply? This implies f has become purely a function of what? Reynolds number for a constant value of epsilon s upon d. So what he did, he made this constant. He then said f is a function of Reynolds number for a particular value of epsilon s upon d. Then he got a particular curve. Let us say he got this particular curve. Let us say he got this particular curve. And that was for which value? Epsilon s upon d equal to 0.005. Next, he made a different constant. After making a different constant, he got a different curve. Let us say this curve was for which value? 0.002. Likewise, he took different values of epsilon s upon d. He got different curves. All these curves. Whereas over here I'm having friction factor, over here I'm having Reynolds number. This is F, this is Re, and along all these curves, who is constant? Epsilon s upon d is constant. Now imagine I come up to you and I say that epsilon s upon d is equal to 4 into, let us say not 4 into, 4 into nahi hai yahan pe. Let us say 5 into 10 power minus 4. I say 5 into 10 power of minus 4, and the value of Reynolds number is equal to 6 into 10 power of 7. I want the value of F. I want the value of F. Going to the formula, applying all those things, complicated. उससे अच्छा क्या करेंगे हम अब? We will use this particular graph. Don't worry, in examination, nothing like this will happen to you. I'm telling you, this is a part of your curriculum, so you should know what Moody's diagram is. What you'll do, you will first look at this value. अब देखेंगे आप 5 into 10 power minus 4 कहाँ पे? यहाँ पे 5 into 10 power minus 4 है. You will go along this line. You will just, everything is blank now for you. Only one line is existing. Which line is existing? This line is existing for you. Then you will see where is the value of Reynolds number 6 into 10 power 7. Let us say this is log table. Okay. So this is 10 power 7. This is 10 power 6. So this is 2 into 10 power 7, 3 into 10 power 7, 4, 5, 6. This is 6 into 10 power 7. You will go along this particular line. You will go along this particular line. You will go along this particular curve. You will see where these two things are merging. They are merging over here. They are merging over here. Then you will identify the corresponding value of friction factor from here. Let us say the friction factor 0.017. Some value I'm taking 0.017. You will get the value. Okay, TK. These two things, if I'm merging over here, I'm getting 0.017. I hope you are following how to use this Moody's chart. If you're doing your masters in if you're doing masters in thermal or masters in anywhere where you're having advanced fluid mechanics, that time you'll have to deal with Moody's diagram. In general, when we were doing our masters in turbulent flow, we don't go for all those formulas. Straight away Moody's diagram dekhte, and we find all these values by taking the value of epsilon s1 d and Reynolds number. Similar kind of thing, mind you, similar kind of thing is there in your thermal engineering also. आपको याद होगा थर्मल इंजीनियरिंग में Moyle's diagram है. Moyle's diagram. In Moyle's diagram also you'll have something like this. You might have done those things. है ना? In even civil, in steel tables, you will have something similar. You will have to go in this particular format. I hope the Moody's diagrams concept is clear to all of you. First go along epsilon upon d's constant value, then friction factor. दोनों कहाँ पे merge हो रहे देखिए. Correspondingly आप फिर देखिए vertical में क्या position है उसका. You'll get the value of friction factor. Clear, I hope. Okay. So this is regarding the concept of Moody's diagram. You will find many Moody's chart in your YouTube, Google पे आप देख लीजिए images में, you'll get many Moody's charts. Last thing, aging of pipes. Aging of pipes. Remember one thing, whenever these commercial pipes age, their surface roughness should increase. Why will the surface roughness increase? Because corrosion will take place, because accumulation of dirt particles will take place, so surface roughness will increase. So due to aging of pipes, surface roughness increases. Surface roughness increases. Okay, ठीक है, यहाँ तक ठीक है. Now what is the increase in surface roughness going to do? What will happen due to increase in surface roughness? Automatically, if surface roughness increases, the capacity of a pipe to deliver discharge will decrease. Example, if you are if you are in places which are closer by to sea, in those places this case will be very significant. Okay, Chennai, Mumbai and all, you'll be finding this particular case. Water sometimes in very old pipes comes out in a rusty form. Colored water, rusty water comes out. Zang khaya hua pani आता है ना? Because pipes are older, over there corrosion takes place very fast. You see, places nearer to sea, corrosion takes place very fast. So what happens, if you open the tap, water in rusty form comes, and that too the water is going to come out very less quantity of water is going to come out. Over a period of time, the capacity of the discharge over there is going to become lesser. Okay, so what is going to happen due to roughness in pipes? Friction factor sorry, due to aging in pipes, friction factor increases. Friction factor increases, leading to decrease in discharge delivery capacity of pipe. Decrease in discharge delivery capacity of pipe. Leading to decrease in discharge delivery capacity of a pipe. The formula over here is given by dF by F is equal to minus 2 times dQ by Q. Minus over here is decrease. So rate of increase in F is equal to 2 times the rate of decrease in Q. This is the formula you're supposed to remember. Okay, with this, we complete the chapter on turbulent flow. Complete chapter on turbulent flow is finished. Okay. Over here, I'm having the slide for Moody's diagram. 1 second, let me delete this slide. After Moody's diagram slide, I'm having the slide for this particular question. 1 second. Yeah, this is a particular slide, aging of pipes. Chali, you have anything to ask? You can raise your hand. Anything to ask? Raise your hand, please. Ganesh. Ganesh.
Hello, sir.
Hello.
Sir, I had doubt in that AD's losses, sir, where cross section was increasing, now dou P by dou X is positive.
Okay.
Means,
Huh.
sir, in that case, the particles which are nearby the pipes means
Wall.
at the fixed wall. That theory means they will flow from higher pressure to lower pressure. That is
Yes.
only valid for that boundary outermost particles only, na?
It's peripheral particles or boundary fluid particles.
And generally, the means flow will be taken from higher total head to lower total head.
Perfect.
Okay. Means for that peripheral particles only that theory is valid. Means
see
where pressure higher, they will flow from
complete flow from higher total head to lower total head. Peripheral particles from higher pressure to lower pressure. लिख लीजिए चाहे. If you want, you can write down. Complete flow, higher total head to lower total head.
Okay. Because velocity changes are negligible.
No, not velocity change. At peripheral particles. At peripheral particles, yes. You can say velocity is almost negligible over there.
Okay, sir. And sir, another doubt is that, sir, means for the fluid, how they will come to know that the total head is decreasing there? Means, for example, if we take two cross sections, where the total head is higher than second one.
Don't worry, he will tell you where the flow is taking place.
No, sir. General means microscopic. I didn't understand. Means let's say at first end there may be some velocity and some pressure. Okay. So means flow is taking place means at second cross section there must be means head must be decreasing.
Yes.
It is because of losses.
Yes.
But for that particle, how they will come to know that means the head is means for example at one point energy is E1, then E2 must be less than E1. But for particle, how they will come to know? Means losses are the next step. Means when they start to flow, then losses will take place. Na?
No, see, generally when we say flow is taking place, it is basically between two reservoirs. Example, you are having two reservoirs over here. There are two reservoirs. Automatically, we know that this is having higher total head, this is having lower total head.
Okay.
So automatically, we know the flow is like this. Already head is established.
Okay. Sir, but even after they are placed at equal height, equal altitude.
Okay.
If there is pressure difference there.
If they are having different altitudes, then there is going to be no flow taking place. Sorry, same altitude. If they're at same altitude, flow will not take place. Losses nahi hai abhi yahan pe. If you are having two reservoirs, same altitude, exposed to atmosphere, there is a pipe, flow will not take place. Even though the pressure one place will be high, one place will be less, still.
Sir, then in pipes, how flow will take place even after they are at same altitude? Means naturally, they will not flow.
See, sir, in the case of pipes, you are just looking at a pipe, but you are not looking at the initial position of the pipe. Over here, you will be having a different amount of total head. Later on, you will be having a different amount of total head.
Okay, initial and final positions.
अब देखिए, now you are looking at a horizontal pipe. आप सिर्फ इतना ही देख रहे. You are looking only at this part. But actually, look, where is its initial part? Here. his final part here. So automatically he is having more head over here and less head over here. So automatically
Okay.
flow will take place in this direction.
Okay. Okay. Okay.
You know? Okay.
Okay.
Thank you.
Understood, sir. Thank you.
Surangi Marathe.
Good morning, sir.
Good morning, ma'am.
Sir, I have one doubt in this potential function.
Okay.
Sir, for a potential function to be valid, then omega, it should be irrotational, right?
Yes, ma'am.
Sir, do we have to satisfy Laplace equation also for that? For a potential function to be valid?
Yes, you have to satisfy. You have to satisfy. Otherwise, how will you come to know whether the flow is existing or not? Because you see, omega is equal to 0 is only telling you about rotation, but it is not telling you about continuity equation still.
So, but if we satisfy Laplace equation, then in that we only come to know if it is incompressible or compressible. If a flow potential function, then how come we come to know that flow is valid or not?
See, if he's just asking you whether for a potential function to exist, okay. If it has to exist for irrotational flow, irrotational incompressible flow, then it has to satisfy Laplace equation. If it has to exist for incompressible flow, it has to satisfy Laplace equation.
Okay, sir. Like I solved questions about it now for a valid potential function. So they are telling that it has to be satisfy Laplace equation also. Then only answer I'm getting the answers.
The problem actually is you assume that the flow has to be incompressible, because incompressible flow is a common assumption we are having. So if the flow is incompressible, automatically it has to satisfy Laplace equation. Otherwise, the flow is not valid.
Okay.
Is it not? So you take it for granted the flow is incompressible over there.
Okay. And sir, if same they ask for stream function?
Stream function, even though Laplace equation is valid, then also you cannot say the flow is compulsorily irrotational. It may be irrotational, may not be. It may be possible, may not be possible. Because remember, in stream functions Laplace derivation, we did not go for continuity equation.
Yes, sir.
Do you remember? We did not apply continuity equation over there. We just applied the condition for irrotation over there.
Yes.
So if he says a stream function satisfies Laplace equation, then what is the conclusion you can make? You can make only a conclusion that it may be possible irrotational flow. May be possible. It is not compulsorily an irrotational flow. क्योंकि अभी continuity equation check ही नहीं किए हम लोग. We have not checked the continuity equation. Clear?
Okay, sir. And sir, and one more thing that for in irrotational flow, sir, how will be the streamlines? Will they be curve or something?
Irrotational flow.
Sir.
In irrotational flow, you can have any kind of stream. You can have circular streamlines also are possible. You can have straight streamlines are also possible.
It is not necessary that it will be straight only or circle only, no?
Okay, recall one thing. Free vortex motion, tell me rotational or irrotational?
Free vortex, irrotational.
How are the streamlines? Circular streamlines.
Yes, sir.
Any kind of streamlines are possible. Don't worry. Any kind of streamlines are possible. You can have straight line streamlines. You can have these kind of streamlines also.
Okay, sir, and one last question is there.
Sir,
balloon is there filled with hydrogen of density 0.08 kg per meter cube, and it is supporting
0.08.
It is supporting 50 Newton weight, and air density is given 0.9. So it is asking diameter of the balloon.
For equilibrium to exist.
Yes, sir.
You can apply over here FB over here, weight of balloon over here, and 15 newtons over here.
So tension will be down only, na then?
Yeah, tension has to be down.
Okay.
FB has to be equal to weight of balloon plus 15 newtons. This will be the value. From there you can get the value. It is quite easy only now.
Okay. Yeah. Thank you, sir.
Thank you, ma'am. Saurav Kumar Thakur.
Hello, sir.
Hello.
Good morning, sir.
Morning, sir.
सर ये एलिमेंट्री फ्लो टर्बुलेंट फ्लो के लिए एलिमेंट्री वर्ड क्यों यूज करते हैं?
टर्बुलेंट फ्लो के लिए यूज नहीं करते हैं, इस चैप्टर के लिए यूज किया गया है. क्योंकि हम लोग सिर्फ बेसिक्स ऑफ टर्बुलेंट फ्लो देख रहे हैं। अभी टर्बुलेंट फ्लो इतना डिटेल टॉपिक है, आप जब एमटेक में जाएंगे, अगर एडवांस फ्लूइड मैकेनिक्स पढ़ेंगे तो आप देखेंगे
और
टर्बुलेंट फ्लो में और बहुत कुछ है, लेकिन आपके सिलेबस में सिर्फ बेसिक्स हैं, इसीलिए एलिमेंट्री वर्ड यूज किया गया यहाँ पे।
सर सर फ्रिक्शन फैक्टर आप जो बोले कि
जी।
रेनॉल्ड्स नंबर और रफनेस पे डिपेंड करेगा, सर
जी।
फैनिंग्स पे डिपेंड करेगा।
देखिए फ्रिक्शन फैक्टर का डिपेंड करेगा तो फैनिंग भी डिपेंड करेगा, क्योंकि देखिए
और
फैनिंग्स इज इक्वल टू व्हाट, फ्रिक्शन फैक्टर बाय 4 है, तो ऑटोमेटिकली वो भी डिपेंड करेगा। अगर f इज अ फंक्शन ऑफ रेनॉल्ड्स नंबर इन एप्सिलॉन, f by 4 आल्सो हैज टू बी अ फंक्शन ऑफ रेनॉल्ड्स नंबर इन एप्सिलॉन, तो वो भी डिपेंड कर जाएगा।
सर एक स्लाइड नंबर 2 में डाउट है।
स्लाइड नंबर 1 सेकंड, स्लाइड नंबर 2।
सर इसमें जो इक्वेशन ए आया है,
जी।
सर इसमें एवरेज और टोटल को इक्वेट कैसे करें?
एरिया अंडर द वेलोसिटी ग्राफ। देखिए अब इसके लिए एक सेकंड मैं एक डायग्राम लेता हूँ। आप सोचिए कि कुछ एरिया है ये,
यस सर।
अब मैं बोलूँगा कि इसका एवरेज ये है। कैसे कहूँगा मैं इसका एवरेज ये है? जब इस एरिया के नीचे का जिस कर्व के नीचे के एरिया को मैं लूँ और उसको अगर रेक्टेंगल में कन्वर्ट कर दूँ, तब
Yes,
हाइट
sir.
ऑफ द रेक्टेंगल एवरेज कर जाएगा, करेक्ट है?
यस सर।
तो वही कर रहा हूँ मैं कि इसके नीचे, इस कर्व के नीचे के एरिया को ले रहा हूँ। इस कर्व के नीचे का एरिया कितना है? इंटीग्रल u टाइम्स dt रेंजिंग फ्रॉम 0 to t है।
ओके सर।
ये क्या है? कर्व के नीचे का है। और रेक्टेंगल के नीचे का एरिया कितना है? वो तो है u बार टाइम्स कैपिटल T है। दोनों को इक्वेट कर सकते हैं, क्योंकि अब एवरेज का मतलब क्या है कि जितना एरिया इस कर्व के नीचे है उतना एरिया इस रेक्टेंगल का है। इसलिए दोनों को इक्वेट कर दीजिए तो u बार आ जाएगा 1/t इंटीग्रल 0 to t u टाइम्स dt,
ठीक है सर।
है ना?
और सर वो जो कमर्शियल पाइप के केस में आप बोले कि लैब में जो पाइप बना रहे हैं,
जी
सर
जी।
उसका हेड लॉस सेम कैसे रख रहे हैं जो मैन्युफैक्चर हो रहा है उससे?
सेम रख नहीं रहे हैं, सेम आने जब तक चेक कर रहे हैं। देखिए
तो वेरी कैसे
सेम
कर
हो
रहे
नहीं रहा है। मान लीजिए डायमीटर सेम रख सकते हैं, रख
हैं? यस
सकते हैं।
सर।
लेंथ रख सकते हैं, रख
रख
सकते हैं।
सकते हैं।
क्यों रख सकते हैं? रख सकते हैं। ये तीन हमारे कंट्रोल में है। अब हम क्या कर रहे हैं? अब हम जो है इसको कुछ एप्सिलॉन देंगे। मान लीजिए हमने पहले एप्सिलॉन दे दिया, इसको कुछ 20 माइक्रॉन्स दिया एप्सिलॉन को। इसको हमको पता चला कि इसके अंदर हेड लॉस ज्यादा है, इसके अंदर हेड लॉस कम है।
यस
मतलब
सर।
ये है कि रफनेस बढ़ानी पड़ेगी अब इसमें। इसको 30, हम इसको चेंज करते जाएं। कब तक चेंज करते जाएंगे? जब तक कि ये दोनों हेड लॉस बराबर ना हो जाए। जब हेड लॉस बराबर हो जाएंगे तब हम कहेंगे दोनों के एप्सिलॉन भी सेम हो गए हैं। आर यू फॉलोइंग ना?
यस सर। सर
ऐसे।
पर
हाँ,
पाइप में भी तो डिस्चार्ज वेरी करता है ना हर सीजन में,
हर
यूज पे तो एक
क्या वेरी
डिस्चार्ज के
करेगा?
लिए डिस्चार्ज
डिस्चार्ज तो हम दे सकते हैं ना, वी कैन फोर्स सम डिस्चार्ज ओवर हियर।
तो एक पर्टिकुलर डिस्चार्ज के लिए किया जाएगा ना,
अगर
वरना
पर्टिकुलर डिस्चार्ज के लिए किया जाएगा तो हर डिस्चार्ज के लिए वही आंसर आएगा ना फिर।
न तो फिर सरफेस रखने से चेंज करना चाहिए।
नहीं सर, अगर एक डिस्चार्ज के लिए मेरे को कंक्लूजन आ गया कि इन दोनों के हेड लॉसेस सेम आ रहे हैं इस पर्टिकुलर सरफेस रफनेस पे,
अच्छा।
मतलब कोई भी डिस्चार्ज पे मेरे को वही आंसर आएगा ना फिर।
यस यस
ठीक है ना?
यस सर। और सर और एक क्वेश्चन आप बताए थे किसी को
जी।
कि जिसमें एक पाइप और नोजल लगा हुआ है, तो पाइप पे क्या टेंशन आएगा कि कंप्रेशन आएगा?
हाँ, टेंशन आएगा उसमें।
सर उसमें एग्जैक्टली क्वेश्चन क्या है कि
मान लीजिए कोई पाइप है, उसको आपने यहाँ पे कोई, नहीं पाइप बाहर थी, पाइप बाहर था, नोजल अंदर में था, नोजल अंदर में था कुछ। एक सेकंड, एक सेकंड, एक सेकंड।
हाँ सर ऐसे ही था।
नोजल कुछ ऐसा था। तो इस पाइप पे क्या काम कर रहा है? टेंशन लग रहा है कि कंप्रेशन लग रहा है?
सर नोजल की वजह से कि पानी की वजह
तो ये पानी जब बाहर जाएगा तो नोजल इसको पुश करेगा ना आउटसाइड की तरफ,
से? यस सर।
तो टेंशन आएगा इसमें।
सर तो पाइप पे कंप्रेशन हो रहा है पुश करने
कंप्रेशन, कंप्रेशन क्यों आ रहा है?
सर? अच्छा पाइप पे तो पुश हो रहा है
हाँ।
तो उसको, अच्छा हाँ बाहर की तरफ टेंशन आ रहा है। ठीक है
ठीक।
ठीक है सर, थैंक यू।
थैंक यू सर।